Hello Finxters! Today's topic is a new and interesting algorithm, the A-star algorithm. As a previous algorithm, the Dijkstra's one, this one is also based on selecting the next vertex determined by its total cost, and for that purpose we will also use our famous priority queue. Selecting from a priority queue, just a reminder, means that the vertex with the highest priority and commonly expressed with the lowest cost gets picked first. So maybe a few words to compare this algorithm to the Dijkstra's one. Contrary to the Dijkstra's algorithm, A-star algorithm calculates the priority of a visited vertex as a total cost of the vertex. The Dijkstra took into consideration only how much is the sum of edge weights to reach a specific vertex. But the cost in A-star algorithm consists of the value of its heuristic function, and heuristic function in this case, actually in every case, is an estimation of how distant a vertex is from a target vertex. The cost consists of this value of the heuristic function and the sum of the path weights leading to the vertex. You'll see in a moment what I'm talking about. As usual, A-star algorithm calculates the priority of a visited vertex by assigning it the lowest possible cost. This is an important note to remember, because later you'll see how the algorithm can even update total cost of a vertex in order to bring it to the lowest possible cost. In general, the algorithm will reduce the cost of a visited vertex by an update if it finds an alternative path with a lower total cost. Our target vertex, as usual, is marked as 6, and the starting vertex is marked as 5, also with an assigned cost of 10. This total cost of 10 and the heuristic value of 10 means that its total cost is not dependent on any edges preceding them, because it has no edges. I mean, its starting vertex, it cannot have any edges leading to it. The story starts with it. One more thing, our other vertices costs are currently set to infinity. Although we know their heuristic function values, we don't know what edges we will take to get to them, and therefore we still don't know what is their total cost. Anyways, the edge weights are indicated above each edge. Let's start with the starting vertex. It's marked in light blue color, and it's queued with a calculated total cost written as the right element in a tuple. When a vertex is explored, all its previously unqueued, unexplored children are put to the priority queue. So this algorithm starts by visiting the starting vertex with the highest priority or the lowest cost, and in our case that's the only vertex in the priority queue with his total cost of 10. By exploring the starting vertex, we will discover and visit vertices 0 and 3. And also one thing to remember: after we explore a vertex, in this particular case vertex 5, it gets removed as indicated by this red line. It gets removed from the priority queue. You cannot see it here anymore, and its children vertices 0 and 3 are added to the priority queue, and their priorities or their total costs are calculated. That's the thing we'll do next. The total cost of a vertex is calculated in a very simple way. You just take a look at its heuristic function value, at its estimated distance to the target vertex. For vertex 0 this is equal to 4. So 4 plus 4 equals 8. We are always looking to the connecting edges all the way to the starting vertex. It's 8 in total cost for vertex 0. And let's see the same thing for vertex 3. Its heuristic function value is 7, and the weight of the leading edge is 2. 2 plus 7 equals 9. Now let's see which one of the vertices in the priority queue has the lowest total cost. It's vertex 0. Its total cost value is 8. The total cost of vertex 3 is 9, and we're going with vertex 0. By exploring vertex 0, it gets removed from the priority queue, and in this case 2 new vertices are added to the priority queue. That's vertex 1 and vertex 2. Their total costs are calculated as 2 for vertex 2, 2 plus 4, and that's 8 in total. The same goes with vertex 1. It's 4 plus 4 plus 4, and that gives us its total cost of 12. Now let's see which vertex is going to be explored next. We have vertex 2 with total cost 8, vertex 1 with total cost 12, and vertex 3 with total cost 9. So we are going to explore vertex number 2, vertex 2. We are pulling it off from the priority queue, and we're exploring it, and this exploration will make us visit vertices 6 and 4, so that's why they are put into the priority queue. Here's the vertex 4, and here's the vertex 6. Their total costs are calculated as follows. The target vertex has its heuristic function 0, and its total cost is calculated as 0 plus 5 plus 2, that makes 7, plus 4, that makes 11, and 11 is here. The same goes for vertex 4. We start with its heuristic function 5, plus 1, we are following the arrows in the opposite direction. 5 plus 1 is 6, plus 2 is 8, plus 4 is 12. And that's our total cost for vertex 4. The next one to be explored is vertex 3. So by exploring 3, we have also previously visited, but doesn't matter. We have also visited vertex 4, and an interesting thing happened. By visiting, and algorithm always tries to update vertex, a total cost of a vertex, even if it was visited before. In our case, the algorithm will see that the heuristic function value is 5, and it will follow the path across 3 over the 3. That's 5 plus 3, that's 8, and plus 2, that's 10. Its new total cost of the vertex 4 is 10, and as I said in the beginning of this presentation, the algorithm will always try to find the lowest total cost of a vertex, and now it succeeded, and this resulted with lowering the total cost and also cancelling, as you can see here, the previous relationship with vertex 2. Previously the vertex 2 was a predecessor to the vertex 4, but now this relationship does not exist anymore, and the predecessor of vertex 4 is vertex 3. Let's continue with the algorithm. The next vertex to be visited, to be explored, is vertex 4. And by exploring vertex 4, we actually didn't discover any connecting, any adjoining visited or unvisited vertices. They're all explored, so nothing to discover here. Vertex 4 just gets removed from the priority queue. The next vertex to explore is vertex 6. So let's do vertex 6. And we should also notice that by exploring vertex 6 we didn't visit any new vertices. So vertex 6 just got removed from the priority queue, but one more thing, as algorithm always does with every vertex, but I'm emphasizing this right now, algorithm always checks if the explored vertex is the target vertex, target entity. Our vertex 6 is the target vertex, and the algorithm signals by recognizing this and gives us as a result a search path found by using backtracking. It goes from the target vertex in reverse following its predecessor vertices, and here we have our search path starting from 5, going over 0, over 2, and over 6. And now that we have arrived to target vertex, we know that the absolute lowest total cost of finding the target vertex is 11. Let's check. It's 4 plus 2, that's 6, plus 5, that's 11. Here it is. One more thing to mention about the arrows. I didn't mention it before, so I'll use this opportunity and explain why do we have the arrows. To simulate a list of mutually connected, explored and visited vertices, we have to keep the track of our path by successively flattening the graph into a tree, as indicated by the arrows. Maybe a quick reminder, what's the main difference for our purposes here between a tree and a graph? A graph can have loops in it. A tree never has a loop. A tree has branches. Our branches are 5, 3, 4, and it ends here. There is no edge, no relationship between the two. The next branch is 5, 0, 1, and the one more branch left is 5, 0, 2, and 6. Incidentally, this is our shortest search path. So this way, if we find the target element, and the A-star algorithm will always find it, the Dijkstra's algorithm will always find it, this way we will be able to backtrack to the starting vertex and reconstruct the search path. You can look about this in more detail in the algorithm. I encourage you to do so. The algorithm is not complicated, but it's very interesting. I mean, the entire algorithm, A-star algorithm, is very interesting to learn how it works. And it actually works very similar to something we would do in everyday life. Maybe you didn't think of it earlier this way, but let me try to illustrate. When you're at a starting point and you want to reach your destination, you are inquisiting about which maybe if these are the cities, you are inquisiting about what are the closest cities to your destination. But you also need to know what of these closest cities are the closest to you, not just to your destination, because the total cost of your trip is the cost of reaching a vertex, a city in our example, and then there is also this reminder of the trip which you have to take to actually get to your destination. So in an ideal world, heuristic function values would actually be 100% precise estimations of the distance, and by using that you would always know what is the closest city to your destination, and you would just choose this city. So we had a very interesting story. I would say it was very interesting for me to learn how this algorithm works. I also gave you an example in a hope to help you understand the algorithm better. And that was all from me. And until next time, see you. Bye bye.